Hi, welcome to the first lecture of Geology 108, Crisis of a Planet. Today, we will discuss our origins as far back as we can imagine it, at the origin of the universe itself. Our ancestors have invented many stories of creation. Many enduring myths and legends have tried to address the simplest and most fundamental questions. Where do we come from? How the world around us came to be, and what is our place in the universe? Religion has commonly made these questions at the center of their belief system. In many cases, they have placed humankind at the center of the universe. For example, and despite evidence, religious dogma has postulated that the moon, other planets, and the sun all rotate around the Earth. While this is true for Earth's only satellite, the moon, the rotation of Earth around the sun is key to explaining astrological observations, but also other simple facts, such as the succession of seasons throughout the year and the amplitude of tides. But religious beliefs also applied to the origin of time itself. In Judeo-Christian religions, this happens around 4000 before Common Era. However, nature abounds of examples of much longer processes. Evidence of an ancient Earth can be found in fossils from species that no longer exist, from landforms created by wind or water erosion that takes millions of years to be formed. Think the Grand Canyon. Erosion from the Mississippi River carved through layers and layers of rocks to form this majestic landscape after 5 to 6 million years, cutting through rocks that are themselves billions of years old. In fact, it is geological observations, for example, stacks and stacks of different rocks, documenting epochs with different climates, fauna, and vegetation, that provided clear evidence of Earth's tremendous age. Modern dating techniques place Earth's formation at 4.5 billion years ago. But why should time itself be bounded? Why should there be an origin, a starting point to everything? Could time be infinite? Well, the clearest and most accessible evidence that time has a beginning, a fact that should not be trivial at all, comes from the darkness of the night sky. Imagine us living in an infinitely large or infinitely old universe. In this imaginary world, the light from any star would have had enough time to reach us, illuminating the entire sky with starlight. As this is not what we observe, we can draw the following conclusion. Either time is finite, or the universe is finite, or both. This is a proof by contradiction. This realization was an important clue that eventually led to the Big Bang theory. Until the early 20th century, it was believed that the entire universe was the galactic cluster of stars called the Milky Way. The Milky Way already contains the astonishing number of 100 to 400 billion stars, one of which is called the Sun, and at least as many planets. Technical progress in astronomical instrumentation led Melvin Slipher to discover 12 new galaxies beyond the Milky Way in 1913. Shortly after, in 1920, out of Mount Wilson Observatory, Edwin Hubble identified a total of 39 galaxies, but the pace of discoveries quickly picked up. Eventually, with the advent of space telescopes like Hubble, we tallied more than 100 billion galaxies, each containing about as many stars and at least as many planets. So I'll let you count how many planets exist in the known universe, but it's close to saying a gazillion. These discoveries profoundly changed how we imagine our place in the universe, as the likelihood of finding inhabitable worlds out there, and even worlds with intelligent life forms, is finite. Humankind is definitely not at the center of the universe, and it is unlikely that we are alone in the universe. So modern observations confirmed our old thinking. The universe is finite. However, they also provide clues about the origin of time itself. We can identify distant galaxies because they emit light that travels the interstellar vacuum to reach our eyes or our instruments. Light is a form of electromagnetic wave carried by photons. Just like any wave, it changes frequency as a function of the relative speed between the source and receiver. You can experience this phenomenon with sound waves as the Doppler effect, which distorts the pitch of a sound if the source is coming towards or away from you. Think about an ambulance passing by, for example. All the galaxies in the universe show this effect as a red shift in the light spectrum, indicating that they are all moving away from each other. A red shift in light is equivalent to the lower pitch of an ambulance speeding away past you. This shows that the universe is expanding outward. To simulate the origin of the universe, we can simply imagine playing this movie backwards. If we rewind for sufficiently long, all the galaxies will converge to a single point, a singularity called the Big Bang. The amount of time it will take for the universe to expand at its current rate, which is called the Hubble constant, from a small volume, say just 1 meter, to its current size, provide the estimate of the age of the universe. It is 13.8 billion years. So when the Earth was born 4.5 billion years ago, the universe was already 9.3 billion years old. Another independent observation confirmed the Big Bang. Confirmed the Big Bang theory. In the 1960s, Americans Arno Penzias and Robert Wilson discovered the cosmic microwave background, or CMB, radiation. This is a background radio signal that pervades the entire universe and can be detected from any direction. The CMB shows that the deep vacuum of space is not dead cold with, say, 0 temperature, but is instead filled with microwaves with a temperature of 3 degree Kelvin. That is 3 degrees above the absolute 0 temperature. It is difficult to imagine every place of the universe to have the same energy level unless all the expanse of the universe was concentrated in a single point, which is compatible with the Big Bang hypothesis. The cosmic microwave background, the CMB, represents the oldest image of the universe when it was only 380,000 years old, corresponding to the first time when photons separated from other particles and radiated away. Before that time, light itself did not exist. Modern observations of the CMB show very modest variations about the mean of just 200 microkelvin. These energy fluctuations represent the seeds that grew to become galaxies. Nowadays, we understand the formation of the universe from a combination of direct observations and from the predictions of quantum mechanics, which describes the interactions of subatomic particles. How the universe formed from a tiny point to its current vast expanse is described by the Big Bang theory. We can think of the initial universe being so condensed and hot that it was a very tiny ball of pure, immense energy. For a tiny period of just 10 to the minus 43 seconds, called the Planck epoch, the universe consisted of only one pure form of energy. There was also only one force in the whole universe. The next 10 to the minus 35 seconds of the universe, called the inflationary epoch, expanded the universe to a size of a few meters. As the universe expanded and cooled, the various states of matter, energy, and even forces of nature condensed out, or they came to be. We can understand the formation of matter from energy through the famous equation of Albert Einstein, E equals mc squared, where E is energy and m is mass. That describes the correspondence between mass and energy. As the universe expands, it carries the edge of space with it. Outside of this boundary, there is no light, no matter, no energy, and no time. At this point, matter and antimatter existed in nearly equal amounts. But in the next 10 to the minus 5 seconds, matter and antimatter annihilate, creating a small residual of regular matter, releasing additional energy in the process. Dark matter, which is thought to be the most of the mass of the universe, was also created during that time. After 1 second, up to about 100 seconds, the universe was cool enough that neutrons and protons, the heavy subatomic particles, could finally link up to make the first atomic nuclei. Combinations of neutrons and protons created the lightest elements of matter: hydrogen, helium, deuterium, and lithium. The proportion of these elements was 75% hydrogen, 25% helium, and trace quantities of deuterium and lithium. Same as is found on average in the universe today. This creation of light elements is called the Big Bang nucleosynthesis. For the next 100,000 years, the universe was still too hot to allow atomic nuclei to capture electrons and form whole atoms. By about 380,000 years, the temperature and density fell enough so that nuclei and electrons could combine to make atoms, thus leading to the matter epoch we are basically still in today. The last combination released a burst of energy, the remnant of which is the cosmic microwave background. For the next 300 million years, the universe had dispersed and cooled enough that there was no source of light, a period called the Dark Ages. At the end of the Dark Ages, fluctuations of density of the ambient hydrogen-helium gas caused gravitational attraction, leading to the concentration of matter in vast clouds. Within these clouds, 300 million years after the Big Bang, the first stars were born. The production of galaxies peaked by about 1 to 3 billion years after the Big Bang. While on average the galaxies are moving away from each other, they locally attract each other, forming clusters of galaxies. Our galaxy, the Milky Way, is bound to the Andromeda galaxy, and they may even collide in the distant future. The Milky Way and Andromeda are large galaxies of the Virgo cluster, which is itself part of an even larger cluster named Laniakea. These webs of galaxies are the largest structures of the universe. Galaxies are not uniform in size and shape, but neither are they entirely random in contour. The largest ones are elliptic galaxies that are more or less spherical balls of stars, or all orbiting the center with randomly oriented orbits. Fairly common ones are disk, spiral, and bar-armed galaxies that are flat and appear to be spinning about a central mass, like the Milky Way and Andromeda galaxies. The center of galaxies gets most of the mass, and it is so huge it forms a supermassive black hole, a mass so large and dense that light cannot escape its gravitational attraction if it gets too close. Galaxies are typically some 100,000 light years across. Our galaxy contains hundreds of billions of stars. However, only a tiny fraction of the total galactic mass is taken up by observed stellar mass. There is an immense amount of invisible mass within galaxies that we call dark matter. Dark matter is undetectable in any wavelength of light. Even though galaxies may be formed by more dark matter than regular matter, the composition of dark matter remains a mystery since its presence is detected only indirectly. The universe has been expanding outward from the Big Bang, and even seemed to have accelerated pace in the last 4 billion years. This is surprising because the gravitational attraction of galactic clusters could only slow down expansion. Gravity could in principle even collapse the universe. This implies that another force is at play, fueled by an energy field called dark energy. Dark energy is a type of force that only acts across galactic supercluster scales, and it may not have been dominant until the universe expanded to a large enough size, some 4 billion years ago. The first solar nebulas were made almost entirely of hydrogen and helium, and the material to make planets was entirely missing. There was no metals, no oxygen. In fact, there was not even any form of chemical reactions. The self-gravitational attraction of solar nebulas made them collapse on their center of mass. As the cloud densified, particles collided, converting their momentum, a form of kinetic energy, into heat. When the temperature reaches about 10 million Celsius, then nuclear fusion starts and a star is born. Nuclear fusion is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei and subatomic particles, neutrons or protons. The difference in mass between the reactants and products releases or absorbs energy, following once again Einstein's formula E equals mc squared, where E is the energy created in the process, m is the mass loss or gain during the nuclear fusion process, and c is a constant equal to the speed of light. During stellar nucleosynthesis, light elements are combined to form heavier elements of matter. Smaller bodies with less than 8% of the sun's mass cannot reach the stage of nuclear fusion at their core. But if the body has sufficient mass, the collapsing gas and dust burns hotter, eventually reaching temperatures sufficient to fuse hydrogen into helium. The star turns on and becomes a main sequence star, fusing hydrogen atoms to form helium atoms in their cores. Fusion produces an outward pressure that balances with the inward attraction caused by gravity, stabilizing the star. How long a main sequence star lives depends on how massive it is. A higher mass star may have more material, but it burns through it faster due to higher core temperatures caused by greater gravitational forces. Main sequence stars fall along a quasi-linear group in the Hertzsprung-Russell, or simply HR diagram, based on the star surface temperature and luminosity, a proxy for size. While the sun will spend about 10 billion years on the main sequence, a star 10 times as massive will remain active for only 20 million years. A red dwarf, which is half as massive as the sun, can last 80 to 100 billion years, which is far longer than the universe's age of 13.8 billion years. About 90% of all stars in the universe, including our sun, are main sequence stars. Stars that deviate from the main sequence are dying stars running out of helium fuel that engage in different types of fusion reactions. Most stars are not isolated in space. About 1/2 of all stars are in fact in double or multiple star systems. In a multiple star system, the stars all orbit about the common center of mass of the system. And this is not accidental because the process of star formation tends to cause many stars to be formed close to each other. In some systems, stars are so close that their surfaces are in contact with exchange of material. So, these exotic extraterrestrial sunsets that you see in movies, well, it's pretty common after all. But now I'm asking you to wonder why our own solar system has only one star. What happened to the other? So if all 4 stars were made of hydrogen and helium, and the basic material to create planets did not even exist, where did it come from? When a small star like our sun dies after running out of fuel, the fusion reaction peters out and no longer keeps the star inflated. The star then resumes its initial collapse. As the collapse is not mitigated by hydrogen fusion, the densification of the core increases the temperature up to 100 million degrees Celsius. At this point, helium fuses into carbon and then some oxygen. The new fusion reactions expand the star many times over, turning it into a red giant. When that process ends, the star collapses again into a small, dense body made of carbon and oxygen called a white dwarf. When a giant star dies, however, the result is more cataclysmic and more productive. Once a giant star has used up its fuel, it also starts to collapse. However, it is so large that the collapse is very sudden and violent, and the rebound of its outer layer creates a massive shock wave and explosion called a supernova. During a supernova, elements heavier than iron are created very abruptly and disseminated to outer space. These elements load the next generation of clouds with heavier dust that will make new solar systems. This time around, the elements required to create rocky planets will be present. In addition, the shock wave created by supernovas plays an important role for the collapse of dust nebulas into solar systems. Otherwise, only the most massive ones could turn into stars, and they are short-lived. The remains of the core collapse into a black hole that is so dense that light cannot escape. The formation of the first stars and then the explosion of the first supernovas occurred early on in the history of the universe, only about 300 million years after the Big Bang. The first supernovas caused heavier elements than helium and hydrogen to come in contact. This was the moment where the first chemical reactions occurred and the first minerals formed, presumably diamonds and graphene, which are made of pure carbon. This was the first step in the mineral evolution and the birth of chemistry. For red supergiants, the entire process of burning through hydrogen to produce elements up to iron is so fast that a giant star finishes its process, uses up its fuel, and explodes to seed many pre-solar clouds in just a few million years. Thus, giant star formation and death can happen many times over and produce enough dusty clouds in a few billion years to allow a solar system to form, as ours did 5 billion years ago. To summarize, the lightest elements, hydrogen, helium, and lithium, were created by Big Bang nucleosynthesis within the first 100 seconds of the universe. Heavier elements were made inside giant stars and disseminated by supernovas. Helium fusion is the basic energy source that powers the sun and thus life on Earth. It is also the power source for the activity of the oceans and atmosphere, including sea currents, weather patterns, and even climate variations. The burning of hydrogen is slow and will last about 10 billion years for our sun, a period we are about halfway through right now. In 5 billion years, when the sun will have consumed all of its fuel, it will expand and consume all the solar system, and then collapse again into a white dwarf. This scientific story is the formation of the universe, which challenge you to think of vast territories of space, of epochs infinitely short and long, and of processes that are far from your daily experience. This is the Big Bang Theory. It explains our origin 13.8 billion years ago as a tiny ball of extreme pure energy. The Big Bang theory cannot yet explain why this singularity took place and what was before, even though the concept of time itself is not really applicable anymore. The Big Bang theory also points to some severe limitations in our knowledge of the laws of the universe, as dark energy and dark matter play an important role and yet escape our direct perception.